Hello everybody, and welcome back for another geometry lesson. Today we're taking a look at the areas of circles and sectors. So let's get started. First things first. Let's say we wanted to find the area of a circle. What does that mean? Well, the area is the space contained inside a circle. And you may know this formula for area. Area equals pi r squared. The idea is, if you have some circle, I'll draw a little one right over here, and if you just know the radius, you can figure out how much space there is inside this circle. If our radius was 5, the area would be pi times 5 squared, which is 25 pi. Now, we can use this for a bunch of different things, but let's start by actually checking out exercise 1. Exercise 1 asks us to find each measure, and we start finding the area of a circle with a radius of 2.5. Well, the area of a circle can be given by the formula pi r squared. And since our radius is 2.5 centimeters, the area of our circle is whatever pi times 2.5 squared will be. To figure out 2.5 squared, we can just plug it into our calculator, just like so. We get 6.25. So, our area is 6.25 pi. But if you wanted to calculate what this would be, we can also just do 6.25 times pi and see that that's going to be 19.64 for our area. Now 19.64 what? And we have to be careful this time. Sure, centimeters is what's given to us, but just writing centimeters is no longer enough. See, our radius, that being 2.5 centimeters, is being squared. So because our unit is being squared, it's 2.5 centimeters squared, we write a square next to our unit. Let's take a look at part B. Now this one's asking us to find the diameter of a circle with an area of 113.1 square centimeters. We don't have an area formula that involves our diameter, but we can be creative. The only area formula we have is pi r squared. But we know that a diameter is just twice a radius. So if we can solve for r, we can multiply it by 2 and get our diameter. So let's see how we do that. Since our area is 113.1, that's what we set on this side of the equal sign. Then we have pi r squared. To start solving for r squared, we can get rid of this pi by dividing it on both sides. In other words, we end up with 113.1 divided by pi equals r squared. And how do we get rid of a square? We can take the square root of both of these quantities. So we get the square root of 113 over pi equals the radius r. Once again, we can plug that into our calculator to solve it. I'm going to type it in as a fraction, since that's what looks nicest to me. Of course, I won't have a y, and a theta there. I think I may have messed up that, but there we go. So, the square root of 113 over pi is 5.997, or about 6. Our radius is about 6. Since our area was in square centimeters, our radius is 6 centimeters. But we don't want that, we want the diameter. So all we need to do is multiply this by 2. If our radius is about 6, our diameter is about 12 centimeters. Very nice. Let's take a moment to take a look at our next definition, population density, a thing which many of you may not have expected to come out of a section on area, but it absolutely comes into play. Let's talk about what population density is. Population density is essentially just going to be a ratio describing how many people live in a certain area. Population density is a measure of how many people live in an area. One example might be if you were looking at an apartment building. Apartment buildings typically have a lot of people in it, so it'd have a very dense population because they're all pretty close together. Meanwhile, if you were looking at a rural area, the population would not be very dense, it'd be very spread out. This comes into play if we take a look at a city. So let's pretend for a second that every dot I make on here is somebody's house. I'm going to place a whole bunch of dots around to make up somewhat of a city. Clearly this city didn't plan the roads very well because this just looks like a random mess of dots. But, you know, maybe it's New England City. We've got all these dots around here that each represent someone's house. And as we get further and further away from the center of the city, the houses get more and more spread out. So the population density isn't the same all the way throughout the city. Like if we take a look here in the middle, there's a lot more density. If we take a look on like the outside, there's less. To find the population density of an area, researchers will typically pick an area to examine. If I wanted to find the population density of the center of the city, I would pick a spot in the center of the city as the center of my data. From there, they would pick a certain radius, for instance, out from that center. For me personally, I want to find the population that's all within this radius right here. Let me draw it out. And they would find how many people are in this area and divide it by how big the area is. So that's what population density is. It examines how densely packed people are in an area. The formula for population density is this. Density equals the number of people divided by the area that we're looking at. Density is the number of people divided by the area. So if there were 5 people in 5 square miles, 5 divided by 5 is 1. We'd have a population density of about 1 person every square mile. So here's a fun fact. I'm not actually from Bloomfield originally. I'm from West Bloomfield. And so when I got here and I started to learn that Bloomfield isn't really a city very much, I was sort of shocked. I was like, what do you mean there's no city of Bloomfield? Well, it turns out that when people refer to Bloomfield, they're referring to a bunch of different places all put together. They're referring to Bloomfield Township and Bloomfield Hills. A lot of times they're referring to Sylvan Lake and Keego Harbor as well. So it's a bunch of spots. In 2022, around 45,450 people lived within 3.143 miles of the center of Bloomfield. The center of Bloomfield, from what I could tell, is around Long Lake and Woodward. Let's say we try to find the population density per square mile. Well, we know that density is a number of people divided by an area. Since we're asked to find the population density, do we know the number of people? Yeah, it's 45,450. But do we know the area? We don't. We do know that all these people lived within 3.143 miles, but that's not an area. What that's saying is, if there was a circle that we were looking at, for instance this one here, from the center of the circle to 3.143 miles, that is the distance we could be. But we could be anywhere in this space. So we end up with a circle with a radius of 3.143. This is where the area of a circle comes in. The area of a circle with a radius of 3.143 is pi times the radius, then square it. We can put in our calculator pi times 3.143 squared. Pi times 3.143 squared. And we get the area as 31.03. It turns out this area of Bloomfield is about 31 square miles, which seems like a lot. That means we can figure out exactly what the population density of Bloomfield is. Take your number of people, divide it by the area, and we get 1464.71. There are 1,464.71 people per square mile in Bloomfield. About 1,465. That's a lot of people per square mile. It turns out that Bloomfield is pretty packed. But you know it's not as packed. Specifically, Bloomfield Hills. Bloomfield Hills is mostly subdivisions and woodland. So the population is going to be more spread out. Bloomfield Hills only has a radius of 1.267 miles, and yet their population density is almost half that of Bloomfield. It's only 870 people per square mile. From these statistics, I want to figure out how many people live in Bloomfield Hills. So how do we accomplish that? Well, once again, density is the number of people per area. This time we are given the population density of 870. So we could say 870 equals. We don't know the number of people, so I'm going to call that variable n. And we don't know the area of Bloomfield Hills specifically. That's another thing we'll have to find out. Thankfully we got the radius, right? So the area of Bloomfield Hills is going to be pi r squared. Pi times 1.267 squared. If I plug that into my calculator, I end up getting the following. About 5.04 square miles. It is so much smaller than Bloomfield. But we can now solve. To solve for n, folks, remember, we can multiply by the denominator to get rid of it. So multiply by 5.04, and we should get our population. Take our answer, multiply it, take 870 and multiply it by our answer, and we end up getting that the population of Bloomfield Hills is about 4,387.55. If we really wanted to estimate it, since we can't have 0.5 of a person, we could say there's about 4,387 people. You could also round up in this case. Both would be appropriate since we don't know if there's going to be a little bit more than half, a little bit less than half. With this being so close, it really would make sense either way. Depends on how accurate you want to be. Let's take a look at our last definition for today, folks. Our last definition is the sector of a circle. Now, when we talk about a sector of a circle, I want to do a little bit of review about what we learned last class. So last class, we learned that we could compare an arc's measure to an arc's length. Let's call these points A and B. We know that a full circle is 360 degrees, so maybe let's say that AB is 1/3 of the circle. Let's pretend that this is 1/3 of the circle. If AB is 1/3 of 360, it'd be 120 degrees. What we learned is this same ratio, let's say of 1/3, works even when we are talking about the arc length. So let's say I told you that this arc length was 60 meters. If the entire circumference is 60 meters, and we know that this arc takes up 1/3 of the circle, 1/3 of 60 would be 20 meters. So these ratios could be compared in a proportion. 120 degrees over 360 degrees compares the two different measures. 20 meters over 60 meters compares the two lengths. But the same can be said of our areas. A sector of a circle is a portion of the area that is cut out. Think of it like a slice of the circle. In this case, the sector here would be this shaded area. A sector is a piece of an area, just like how an arc length is a piece of a circumference, or an arc measure is a piece of 360. But the rule is still the exact same. If we think that this sector is 1/3 of the whole circle, and I told you that the area of this whole circle was, I don't know, 90 meters squared, well then, this sector would be 1/3 of 90. This sector would be 30 meters squared. So just like before, we can always compare a portion of something to the entire thing and set up a proportion. That's what we're going to do down here. So the sector of a circle has a much more formal definition that I want to go over, and then we will talk about the formula for it. To start, make a circle with center P. So here's my circle, here's my center, and I'm going to draw 2 points, A and B. A sector of the circle is the area contained when you draw out 2 radii that connect to an intercepted arc. This is our sector. So the sector of the circle is the area bounded, meaning bordered by, 2 radii, whoops, not radii, radii, and the intercepted arc. The formula to find the area of a sector is, hang on a second, this looks just like what we did in 11.1. It's the sector divided by the area equals the arc measure divided by 360. part of the area divided by the area equals a part of 360 divided by 360. We're just setting up a proportion and solving. So, in example 3, when we are asked to find the areas of these sectors, let's look at what sectors they're talking about. The first sector that we should try and find is this tiny sector here. I'm going to color it in yellow so we know what we're talking about. This yellow sector here can be found by using our formula. The formula is the area of the sector divided by the whole area of the circle equals the area of, the measure of the arc divided by 360. Since we're trying to find the area of this yellow sector, I'm going to call it A subscript S, area of a sector. This is the yellow sector that we're trying to find, remember? But in order to solve this, we need both the area of the full circle and the measure of the intersected arc. One of these is super easy to find. I mean, take a look at the diagram. The central angle is 70, so the intercepted arc is 70. It's always going to match. But to find the area of the circle, we will have to use our area formula. Remember that the area of a circle equals pi r squared. In this case, our radius that's given to us is 8, so it's just pi times 8 squared. And since 8 squared is 64, we could write it as 64 pi. Now we can solve our proportion. 64 pi times 70 is the same as just doing 64 times 70 and putting a pi symbol before it. This would be 4,480 pi. And then we end up with our sector's area, the thing we're trying to find, times 360. 360 AS. To solve, we can divide by 360 on both sides to cancel it out over here, and we get the area of our sector equals 4,480 pi divided by 360, which, if we plug it into our calculator, 4,480 pi divided by 360, we get about 39.1. The area of this yellow sector is about 39.1 inches squared. But we're not done quite yet, because we had to find the areas of the sectors, plural. So the area of this second sector is something that we also want to find. This second sector is the one that sort of looks like Pac-Man. Should have drawn that one yellow. But I drew it orange here. We now need to find the area of the orange sector. To do that, we'll use the area of the circle and the intercepted arc USV. I'd like you to pause the video and see if you can find the area of the sector. Pause here and see what we can do. Hopefully you've had a second to pause the video. Let's see about it. There's two main ways to find the area of the sector, one easy, one difficult. I'm going to show you the difficult way first. To find the area of the sector, we need to know what the measure of its intercepted arc is. Well, if this intercepted arc is 70, we know that this big arc, the major arc, is going to be whatever 360 minus 70 is. It'll be 290 degrees. And we can reuse the same area as before. So our formula is the area of the sector divided by 64 pi equals 290 over 360. When we cross multiply, 64 times 290 is 18,560. So we get 18,560 pi by multiplying these two together. And on the other side, I get 360 times our area. When I divide both sides by 360, we get the following. We get 161.97 inches squared. So that's the more difficult way of finding the area of the sector, is to just use the formula again. But we can be more clever than that. Didn't we say the area of the full circle was 64 pi? Well, 64 pi ends up being this number here, 201.06. If we take the area of the circle and subtract just the yellow slice, wouldn't we be left with the orange slice anyways? We could have just subtracted 39.1 from our area and get the same exact answer, just rounded a bit differently. So folks, that is going to be it for section 11.2. Hope you enjoyed and have a fantastic rest of your day.